Wasabi, you guys. Welcome to Integration Bee Training for Advanced. This is 12.3, and we're going to practice more with manual piecewise integration. So we are manually integrating piecewise functions, and in this section we're going to be dealing with composite piecewise functions. Okay, so let's go ahead and get started. Okay, so we have this integral here. And I believe we have to do a little bit of modifications here because we have a log inside of a floor function and we absolutely do not know what to do with this, right? This looks awkward. So how on earth are we going to deal with this? So because it is inside of a floor function, we do have to take into account of this function inside. So we're going to do a lot of work here. Okay, so what I like to do is whenever we have a composite piecewise function like this, I like to make a list. And I'll show you what I mean by that. At the interval 1 to 10, at the interval of 1 to 10, what does that mean? That means that the log of 10, log base 10 of this inside of a floor function, this is going to equal to 0. Okay, and then if x was between 10 to 100, then it would equal to 1. Okay, or you could write you could also write like this so that you don't have to rewrite this function multiple times. You can go like that. Okay, and you don't even have to put at. You could just list this. Just list the intervals. Right? Oh, this is going to equal to 2 actually. Okay. Right, and the reason why, again, if you're not sure like why does this equal to 1 or 2, it's because if you plug in log, let's say like 20, right? Because it's more than 10, because log of 10 is like ln of 10 over ln of 10, which is equal to 1, right? However, note that ln of 100 divided by ln of 10 is equal to 2, because this is 10 squared. Does that make sense? Using logarithm rules. So because this is between 1 and 2, okay, this means that the floor function, taking the floor function of this, is going to equal to 1. So everything in the interval between 10 to 100 is going to equal to 1. Okay? That's how I see it. That's how I'm listing things so quickly. Okay? And so with that mindset, we finished our list because it only goes up to 1,000. All right, cool. Let's go ahead and split this integral from 1 to 10. We have dx x plus 0. Okay, so this is just 1 over x. From 10 to 100, we have dx x plus 1. From 100 to 1,000, we have dx x plus 2. Right, and then you go ahead and integrate this, you get something like ln of 10 plus the ln, this is minus 10, so that's going to give me ln of 100, and then ln, no, that's wrong, that's incorrect. Ln of 10 here, and then we have ln of 101 minus ln of 11, so I'm just using log rules here. We have 1002, 102, something like that. Yeah, this is our answer. Okay, not a pretty answer, but at least you get the idea of how to solve something like this. Okay, so this is how we solve composite piecewise functions. We make a list. We make a list so that we keep track. It helps us easily keep track and quickly solve this integral. Okay, the function inside here at certain intervals, it's going to equal to this. Okay? All right, let's move on to the next example. What now? How do we solve this? Again, list. Make a list. We make a list. Okay. So it seems that we have x to the power of 1 over 10. Okay. So how do we make a list? How do we make a list? This is a very awkward function. I'm not too familiar with this function, so how do I know what this is? So what you do is, well, 1 to the power of 10 is equal to 1. Okay. 2 to the power of 10. What is 2 to the power of 10? That's like 500. Let's see, 32, 64. I'm not a math Olympiad, so I have to do this by hand. 64, 128, 256, 512, 1024. Okay. So 1024. And then 310. What is 3 to the power of 10? I don't know. Right? That's too big for me. However, we can go ahead and compare. We can compare 3 to the power of 10 and 2020. So 2020, I know this is literally 2 times 1010, or I guess, sorry, I could rewrite this as 20 times 101, right? Is that how that works? 101? Okay. Here we see that this is literally like 81 times 81 times 3 to the power of 6. Okay. Because this is 81 is 3 to the power of 4. So, oh, I'm sorry. Then in that case, it's just this. 81 times 81 times 9. Would that be correct? And then we know 81 times 81. Well, we know that 80 times 80 is going to equal to 6,400, right? So this is obviously bigger, way bigger than 2020. Okay, so that's what we're going to stop. So what that means is that at 2024, so if I let x equal 1024, right, this means that 1024 is equal to 2. Okay, keep this in mind. So at 1024, the 10th root of 1024 is equal to 2. So what this means is that we're going to have to split this up from 1 to 1024. And that's going to give us dx over 1 plus, and then 1024 to 2020 dx over 2. Okay? Oh, well, that's just basic integration. So this is just, this equals to 1023. Be very careful. Plus, and then a half of 2020 minus 1024. So this whole integral, that's like what? 996, 498 plus 1023. So our answer is 1521. Okay? So that is our answer with this. So again, you don't have to, sometimes when you deal with like a big value, you can compare instead rather than actually calculating. Okay? And another thing is, when you're dealing with an awkward function and you're just like, I'm not familiar with this, start testing some values, right? Do the opposite, because the opposite is what you're gonna plug in to x. Okay? And the values, that value is the value that you need to split the bounds. Okay? All right. To the next integral we go. This looks a little intimidating because we have like multiple composite functions inside of a floor function. So how do we deal with this? Okay, well, first of all, let's do a u substitution because, 1 over x and our bounds is like 1 over something. So let's do a u substitution just to give us comfort. Okay, I don't think that's, there's nothing wrong with that. The only thing about that is that now we have a u square in our function. Okay, that's all right. So I just want to make sure that this is a floor function, that's a parentheses, floor function. Okay, so now what? Well, I mean, we have a floor function here, so let's just deal with that first, right? Okay, so we're taking small steps. That's good. It's a very good thing to take small steps. So here at 2 to 3, our floor function is ln of 2. So it's just, it's just going to be 2. So you square from 3 to 4, ln of 3. Okay, cool. And you know what to do here, right? You just compute. Okay, this is 0. Thankfully, this whole thing is 0, because ln of 2 is like 0.693 something. Okay, and if you don't know that, think of e, right? E is 2.71. So if e is 2.71, 2 is less than e, which means that ln of 2 is less than ln of e. And if ln of e is 1, then this is less than 1. Therefore, that whole floor function is going to be 0. This whole integral is 0. And so now what we have here, okay, right, e squared is definitely bigger than 3. E squared is definitely bigger than 3, right? Because e squared is 2.71 squared. That's, clearly bigger than 3. So, because of that, we know that this is definitely between 2. ln of 3 is less than 2. So because of that, this floor function is going to equal to 1. This is 1. So what we have is 3 4 du over u squared. And then, 1 over u, you could just simply solve this. This is 1/3 minus 1/4. Yeah, I just had to be careful because the negative sign. And so now our answer is 1/12. Okay? Again, right, this looked intimidating, but look how easy we solved this, right? Taking small steps, even though we take small steps, it gives us a huge advantage solving this integral very fast. Alrighty, these integrals are getting harder. So how do we deal with these integrals? How do we deal with this integral? Now we have from 1 to infinity, and you're probably thinking, hold up, from 1 to infinity, how are we going to manually integrate this? Okay, don't freak out. Do not freak out. First off, we need to take care of this inside here. Okay, so what I'm going to do is I'm going to let u equal 1 over x minus 1 over 2021. Okay? Now, with some manipulation, let's understand that u plus 1 over 2021 is equal to 1 over x. Okay? I just want to keep that in mind. And so now, by doing with the substitution, if we plug in 1, we get like 1 minus 1 over 2021. So that's going to be 2020 over 20. Oh, but then it's going to be on top. And the reason is because, if you do the derivative, the negative switches the bounds. Okay? The negative would take care of that. Infinity, that's just going to be 0. We get negative 1 over 2021. And then we get, plugging things in, we have du and then x squared, pretty much. However, what is our x squared? 1 over x, that's going to be x squared. I believe, am I doing this correctly? Did I do this correctly? Let u equal, let's see, because if we derive it, we get du equals negative 1 over x squared. This negative is going to take care. Oh, okay. So that x squared is going to be x squared du dx. And we're going to use this x squared as x is equal to 1 over u plus 1 over 2021. Right? Isn't that what this is? And so with x squared, I believe... Oh, okay, yeah. X squared, and so you shove it in, okay, and then it does become at the bottom. Okay, so I had to be very careful. I rather be accurate than to get a wrong answer. Okay, so we do end up with this. Cool. And then of course, you know, based on splitting the bounds, using this ceiling function, we get that at from 0 to 2020, 2021, we should end up with, I believe, 1. Yeah. So it's just 1 at this interval. Which equals to 2020, 2021. And so that's going to be 2021 squared. I'm just doing algebra manipulation just to make things cleaner. We do have 2021u plus 1 squared. Okay. And then, I mean, let w equal 2021u plus 1. And we will end up getting 0, 2020. Oh wait, 2020 plus 1. Oh, 2021. Okay. And then we end up 2021 left over here. dw w squared. And so it looks like this is going to give us 2021 from 2021 minus, it's going to be, because it's going to be 1 over w. Right? Oh, I'm sorry. I was so confused. I'm like, wait, doesn't this diverge? That should be a 1. So now, okay, now everything converges. So now it's just 1 minus 1 over 2021. Okay? And then, of course, simplify this. Your answer is just 2020. Okay? So your answer for this integral is 0 to 2020. Okay? This integral, I believe, is also from Harvard MIT, I think. I think it's from Harvard MIT Integration Bee, which is why it has the year 2021. I think now it's time to get to the advanced level listing here. So, oh boy. I think we're ready enough now to tackle this integral. So, this is, of course, you see 2021 here. This integral is from UC Berkeley Integration Bee, and I decided to invent the traditional use of using GCD. So I came up with the idea of using GCD into integrals, and then my friend Anand, the founder of UC Berkeley Integration Bee, helped me how to converge it, how to use GCD properly into integrals, and to use it properly, you must use ceiling functions or floor functions in order for this to actually integrate, because GCD is only for integers. Okay, so now that we have GCD, I'm sorry to all speed integrators, but I don't know why young me decided to add in a GCD into integration. But now that we're going to come across this in future integration bees, how on earth are we going to tackle this? So it's not easy. I'm going to let you know right now. I'm brutally honest with you. This is not easy to deal with. So first off, these are scary. Log 20 and log 21. Again, I like to convert it or think of it as this, just because it's just easier and less painful. Okay, so that I know, okay, so I'm looking for powers of 20 or powers of 21. Okay, cool. So how do we so now we must start listing. Okay, so from 0 to 1, actually let me color code this. from 0 to 1, okay, we're going to have the GCD of, well, between 0 to 1. We can't actually plug in 0, but from 0 to 1, we know that this is going to be GCD of 0 to, again, 0 plus 1. So from 0 to 1. And the reason why this is going to be 0 is because anything less than, if we, put in like fractions, any fractions less than 1, it's a negative number, right? It's a negative number. And so of course at the interval from 0 to 1, it's a negative number. But because of this ceiling function here, it rounds it upwards. And so because of that, it's going to give us 0 instead of like -1. So we end up with 0 and then 0 plus 1. Don't forget about that plus 1 here. So GCD of 0, 1 is equal to 1. Okay. And the reason why this is equal to 1 is because 1 can divide 0, technically, by definition. Okay. So, okay, we have that. Cool. And now we must do other intervals. Okay. 1 to what? So what's my next interval? So of course we have 1, but then what's my upper bound? My next upper bound, what is it going to be? So, of course, seems like we can plug in 20, right? Because if we let x equal 20, that's going to be an integer, right? So 20 is going to be my next interval, my upper bound. So from 1 to 20, it seems that we have the GCD. The GCD becomes, let's see, at the interval between 1 to 20, we get 1, and over here, this is also, let's do 1, yeah, plus 1, so we get 2. So because of that, the GCD of 1 to 2 is equal to 1, because they're prime, they're relatively prime. Okay, 20 to what now? 21, right? Our next number 21, because now this is an integer. So 21. And now, from between 20 and 21, we know that this is going to be greater than 1, so this is going to be 2, right? Yes. And then here, it didn't surpass 21, but it's getting there. So this still stays as 1. Plus 1, 2, that's equal to 2. Okay, next. 21 to, what's my next number? 20 square. 20 square, right? We need 20 square. That's going to give me an integer of 2. 20 square is 400. Okay, so that's going to give me what? So I didn't surpass 400, so I'm still at 1. So, oh, no, I'm sorry. I'm still at 2, because this is a ceiling function. So 2. GCD of 2. However, now, at this interval, this log surpassed 21. And so now, at that interval, this is going to equal to 2. Plus 1, 3. So that's 1. Okay. 400. All right, but what's my next bound? 21 square. Okay, what's 21 square? 441. All right. So now here at 400, now I surpassed 400, and so now it's 2 point, if any number between 400 and 441, putting it here, I'm gonna get like 2 point something. Ceiling function it, rounding it up, I get 3. All right. 441, I didn't surpass 441, so I'm still at, let's see, 1 point something, right? With ceiling, that's 2, plus 1, that's 3. So we get GCD of 3, 3, which equals to 3, okay? And then we keep going, I know, but we have to keep going to that upper bound. It's okay. All right, so now we have to do 20 cube. What's 20 cube? 20 cube is 8,000. So thankfully, that's beyond our bound here. So we could just stop at 2021. Okay, awesome. So now at here, we surpassed 20 square, of course. So this is going to equal to 3. This portion is going to be equal to 3. And now that this one surpassed 441, this is going to be, this interval is going to give like 2 point something, which rounds it up to 3 plus 1, 4, which is now back to 1. Okay, cool. Our list is done. Holy hell. Okay. Jesus Christ. Our list is done. Unfortunately, we're not done yet, because now the tedious part is still here. We have to sum it. Sum everything. From 1 to... I'm sorry. From 1 to 20. Well, yeah, I'm sorry. So I'm going to go from 1 to 20, because from 0 to 1, 1 to 20, they both equal 1. So I'm just going to... I could just combine it. Okay? I just combine the integral, because they have the same function, 1. And then from 20 to 21, we have 2. From 21 to 400, we have back to 1. From 400 to 441, we have 3. And from 441 to 2021, we have 1. Okay, time to sum it up. They're treating us like human calculators. 2, because 21 minus 20 is 1, times 2 is 2. 400 minus 21 is 379. 3 times 41. 3 times 40. Oh, that's just 123. Thank goodness for easy multiplication. That was satisfying. And 2021 minus 441, that's going to give us like 1580, I believe. Okay. And then we add these two together, 22 plus 379. That's like 11, 401, 123, 10, 6, 7, 1703, 401. That's going to give us 2104. Holy Jesus Christ. Okay. So, we got it. We made it through. Okay. So, our answer to that integral is 2,104. Okay. Holy Jesus. Okay. Cool. Thank you for sticking with me. You are now brave enough to conquer any, at least the beginning portion, because we still haven't done the summation yet, right? But now you are a master of manual integration with piecewise functions. Okay, you now mastered how to deal with piecewise functions by manually integrating. All right, so that's about it. I hope this was very helpful. Again, I know it was a lot of techniques to deal with. So I highly encourage that you rewatch the video and try the integrals yourself until you became comfortable with these techniques. Okay? All right. Thank you guys so much for watching, and I'll see you guys in the next video.